Today, we're very happy to have Emily Cunningham giving our CITA seminar. So Emily is a Flatiron Fellow at the CCA right now and did her PhD at UC Santa Cruz. She mostly works on Milky Way modeling. And so today she's going to tell us about testing galaxy evolution models from the Milky Way stellar halo. And just for the people online, if you have a question, please just raise your hand and I'll moderate the questions. So Emily, if you're ready, go ahead.
Cool, sounds good. Everyone can hear me. Sound is good. All good. Is that a yes? Yes, okay, great, thanks. So thanks for the introduction, Jonathan. My name is Emily Cunningham. I'm a Flatiron Research Fellow at the Flatiron Institute in New York City, where I'm calling in from today. I'm so sorry to not be able to be there in person with you all. I was really looking forward to an in-person visit, but alas, the times we live in are not making that very easy. And so I hope to come back to visit CITA in person another time. But thrilled to be able to tell you about my work today from New York. So as Jonathan mentioned, the title of my talk is Testing Galaxy Evolution Models from the Milky Way Stellar Halo. And so to kick things off, I just want to talk a little bit about what the stellar halo is. So we know the Milky Way is a spiral galaxy, and we believe it to be embedded in a huge halo of dark matter. And strewn throughout this dark matter are stars, and this is the component of the galaxy known as the stellar halo. So here I'm showing you an image of a simulated galaxy from the Latte suite. This is actually the Latte galaxy from the Latte suite of Fire 2 zoom-in simulations. And we can see the spiral galaxy that's embedded in this huge, very diffuse, but very structured stellar component. And this is the component known as the stellar halo. So how do we think the Milky Way got its stellar halo? So the answer is primarily through the accretion of satellite galaxies, of dwarf galaxies. So we believe the Milky Way assembled its dark matter halo over cosmic time by accreting smaller dark matter halos, some of which contain dwarf galaxies. And it's the remnants of these dwarf galaxies that make up the component of the galaxy known as the stellar halo. So I'm showing you here the very classic Bullock and Johnston simulations of purely accreted stellar halos onto a Milky Way-like host potential. And we can see that the reason that these stellar halo is so structured is because the dynamical times in the halo are so long compared to the age of the universe and the age of the galaxy. And so as such, we can use the positions and the kinematic properties of halo stars to trace back to their initial conditions. So the kinematic properties and the phase-space properties of halo stars retain a link to their initial conditions, but also, of course, their chemical properties, which retain the imprint of the environment in which they formed, which are smaller dwarf galaxies, in their stellar atmospheres. So the goal of many galactic archaeology studies in the stellar halo is to use the kinematic and chemical properties of halo stars to make inferences about the dwarf galaxy populations that built up the Milky Way's mass over time. And this is not just a theoretical concept in the observations. We have a lot of evidence for this hierarchical galaxy formation in action. So I'm showing you here a very classic field of streams image from the Sloan Digital Sky Survey, where we can see just in photometric data alone, a lot of these overdensities that we believe to be from tidal disruption of both dwarf galaxies. So here, the Sagittarius stream, which is the most massive stream in the Milky Way that we know of, as well as smaller streams that we believe to form from tidal disrupting globular clusters. Okay, so why should we care about the stellar halo? Why is this interesting? I'll tell you why I'm interested, but first I just want to talk about why you could be interested in whatever your scientific interests. For one, the stellar halo contains the oldest, most metal-poor stars in the galaxy. So if you're interested in metal-poor stars, if you're interested in first stars, if you're interested in old, interesting stars, the stellar halo is a great place to look. In addition, it's composed of the remnants of destroyed dwarf galaxies. So the dwarf galaxy populations that contributed to the buildup of the stellar halo are dwarf galaxies that did not survive until present day and that we can't observe directly in the field. But we have this unique opportunity within the stellar halo to study these systems on a star-by-star basis if we can reconstruct where they came from. In addition, we can use halo stars to trace the dark matter distribution of our galaxy and study the mass distribution of the Milky Way, which is a fundamental parameter of our galaxy and a really unique opportunity to study the dark matter distribution in our own galaxy, which is critical. And finally, it provides the opportunity to recreate the mass assembly history of the Milky Way. So understanding both the mass and the accretion history of the Milky Way is critical to place our own galaxy in its cosmological context. And fortunately, we've made a great deal of progress on this topic because we are in the midst of what there have been many conferences that refer to the galactic renaissance, which feels very grand, but what do people mean when they say the galactic renaissance? So if we have this goal of wanting to measure 6D phase space and chemical information for halo stars out to the virial radius of the Milky Way, the good news is that we're there, we're doing it, and we're going to be doing it even better over the coming years. So to achieve this goal, we require deep photometry of the Milky Way. So we have a number of amazing photometric data sets. And of course, critically, Rubin LSST will provide outstanding photometry to really let us look to the edge of our own galaxy. We need astrometry to measure the tangential motions of stars. We are in the Gaia era at present, which has revolutionized our field, and I'll talk a little bit more about that. And down the line, Rubin LSST will, I'm sure, revolutionize our field all over again, as well as proper motion information, very precise proper motions that we'll be able to get from Roman Space Telescope. And then finally, spectroscopy, where we again have spectroscopy from Gaia. We have many follow-up Gaia spectroscopic missions, such as Foremost, DESI-Weave, Subaru PFS, and SDSS-5 coming soon. So it's a very exciting time to be interested in stellar halo because we currently have more data than we could have dreamt of 10 years ago, and it's only continuing to grow. And so a lot of what we've learned from the Gaia era, a lot of what we learned from the Gaia era is that we have even more streams than we thought, than we thought. I'm showing you here the beautiful image of the Gaia image of the Milky Way galaxy with a number of the beautiful streams that were discovered as a part of the S5 collaboration led by Ting Li, thanks to Gaia and follow-up spectroscopy. And so we're discovering all of these new systems. In particular, I want to highlight the emerging consensus in the field of Milky Way studies that the inner halo of the Milky Way is dominated by debris from a single massive accretion event. This is sometimes called the Gaia sausage. This is sometimes called Gaia Enceladus, sometimes Gaia sausage Enceladus. I'll probably stick with that to be agnostic on the naming. But what I want you to take away from this is that this is, a major paradigm shift from the first Gaia data releases, that we believe that most of the debris that we're seeing in the Milky Way halo in the solar neighborhood is dominated by this debris from this one event. But on top of those streams, there are many other substructures that have been discovered and characterized in the halo, from remnants of dwarf galaxies to remnants of disrupting globular clusters, that we have this halo that is rife with structure and phase space. But what remains challenging is knowing how to interpret these findings, and how do we go from seeing a substructure in the data and understanding its origin. And so fortunately, while we've had all of these really exciting advances on the data side and are continuing to have these exciting advances on the data side, we've had advances on the theoretical side as well. So here I'm showing you a beautiful movie from the Latte suite of simulations that I mentioned earlier. These are high resolution zoom-in cosmological simulations. And in these simulations, we've come, they're very different from what we were looking at earlier with the Bullock and Johnston simulations. In these simulations, we have, first of all, a full cosmological context. We have a live disk and a live halo that interact. We have dwarf galaxies that are interacting before they fall in. We have not reality, but we have a realistic setting in which we can test some of our assumptions when we are interpreting the data. So that's how I like to think about my work. I like to use simulations to nail down sort of what questions we should and can be asking of our data, and to think about using simulations to come up with new ideas for engaging with these exciting data sets. So that leads me to the outline of my talk today, which has two parts. So in part one, I'm going to talk about using halo stars to learn about our own galaxy, the Milky Way, and to study the dark matter distribution and disequilibrium in our own galaxy. And then in part two, I'm going to talk about how we can use halo stars to learn about the dwarf galaxies that contributed to the buildup of our own galaxy, the Milky Way. And I want to, of course, thank all amazing collaborators who've contributed to this work, in particular graduate students. So Alex Riley is a graduate student for another, I think, week, 2 weeks, Danny Horta for another 2 months, but also Nand Panithan-Baisal, who is an amazing grad student at UPenn. So I want to thank them in particular for their contributions to this work. So I've talked about our general picture of the Milky Way, and I've left out a really important part of our general context in the Milky Way, and that's the Large Magellanic Cloud. So when I'm talking about dark matter distributions in the Milky Way, it's critical that I mention the Large Magellanic Cloud because the LMC is the Milky Way's most massive satellite. So our classical picture of the LMC is that the LMC is a dwarf galaxy, at 50 kiloparsecs. Classically, it was believed to be about 10 to the 10 solar masses, which is about 1/100th of the estimate of the virial mass of the Milky Way. So relatively small compared to the Milky Way. And then it was happily just going around the Milky Way on a 2 gigayear circular orbit. And so this was the classical picture up until, 2006 of the LMC. But there was this fundamental uncertainty in studies of the LMC on its tangential motion, because it was only up until recently that we've been able to measure tangential motions and proper motions of stars in our own galaxy outside the solar neighborhood, as well as dwarf galaxies. And so the real revolution came when the LMC's proper motion was measured using archival data from the Hubble Space Telescope. And so this was work led by Nitya Kayavailil, who found that the LMC was moving very near the escape speed of the Milky Way. Once she was able to measure its proper motion, it became clear that it was moving much too fast to be on a happy little 2 gigayear orbit, just sort of going around the Milky Way. And this changed, the whole field around the Large Magellanic Cloud and created this first in-vol picture where we believe the LMC is on its first interaction with the Milky Way, rather than having orbited it for many, many years, gigayears. So in addition to this revised first in-fall picture, there's also increasing evidence that the LMC is likely quite a bit more massive than we thought previously. So, I mentioned the classical picture, the LMC was about 1/100th of the mass of the Milky Way. But there is mounting evidence from a number of different studies using a number of different techniques, including, modeling the rotation curves, abundance matching, based on its satellite populations, modeling of the full Magellanic system, and also, perturbations to tidal streams led by Nora Ship. We have just a lot more information to lead us to believe that the LMC is probably between 10 and 20% of the mass of the Milky Way. And so this is very serious for doing dynamics in the Milky Way. And this point was made, way back in 1967. This wasn't necessarily a new point. So I love this abstract from Abner and King that lays out that contrary to the widely held belief, the gravitational effect of the Magellanic Clouds on the Milky Way is indeed serious. And this was true. This is what they thought was true for the classical picture of the 10 to the 10 LMC. For 10 to the 11 LMC, it's even more complicated. So what are the implications of this, of a massive LMC for the dark matter distribution, Milky Way? So I want to highlight here amazing work from Nico Garavito Camargo, who is my colleague at the CCA, where Nico ran a number of very tailored n-body simulations of just a Milky Way falling into of an LMC falling into a Milky Way, and found that the LMC is predicted to induce a wake in the dark matter halo. And so what do I mean by a wake? So here in this image, these colors are showing over and under densities. This red line is showing you the orbit of the LMC. The position of this LMC is this red dot here, and the position of the Milky Way is this blue disk here. And so what Nico found is that there are two components to this wake. The first is this overdensity that's trailing the LMC in its orbit. So this we can think of as the classical dynamical friction wake, where dark matter particles feel the immediate gravitational pull of the LMC. They're accelerated to follow the LMC in its orbit, and this in turn exerts a drag force on the infalling satellite. We also see this overdensity opposite to the LMC, and this is a result of this modal response of the full dark matter halo. So even in this simulation where we just have two bodies, we get this very complex result. In addition to these over and under densities as a result of the wake, Nico also found that the LMC is inducing a reflex motion on the Milky Way. And so what this means is that as the LMC is falling in, and as it gets closer and closer to the disk, the LMC actually dislodges the disk and the inner halo from the center of its dark matter halo. So the center of the inner halo is no longer the same as the center of the outer halo. And so of course, if we want to do dynamics in the Milky Way, this has huge implications for how we should be modeling orbits in our galaxy if we can't even really nail down where we should be putting the center of the dark matter distribution. And so this is a really exciting result that Nico has found in the simulations, but of course we want to test these results in observations. This is primarily studied in idealized n-body simulations so far. So we have predictions on the theoretical side that there are these large-scale perturbations to the Milky Way's dark matter distribution from the Large Magellanic Cloud. But it's not the only source of disequilibrium in the halo, because we also believe the halo to be formed primarily from tidally disrupting satellites. So we have disequilibrium on different spatial scales. So here I'm showing you two maps. The left-hand side is a map of Nico's n-body simulations of just an LMC in a Milky Way. And each little pixel is color-coded by the velocity and isotropy. So you can see you have these large-scale features in the velocity field. But on the right-hand side, we have a map of the stellar halo from the fire simulations. This is the M12M halo for those who know the fire halos, where each grid in this map is color-coded by the same parameter, the velocity and isotropy. And we can see that we have these features in the velocity field that arise due to substructure in the halo, because we have unphase mixed substructure as well. And so what question that we had was, how do we disentangle disequilibrium on different spatial scales? If we want to measure this effect from the LMC, what do we do about the fact that we think there's all of this substructure in the halo? How can we disentangle these two effects? So this led to a paper that I collaborated with Nico Garavito-Camargo on, where we used spherical harmonics to disentangle the velocity perturbations on different spatial scales. So just to remind you, I had to spend a lot of time on Wikipedia relearning about spherical harmonics when I started this project, because it had been a minute. So I'm going to put it up here for me, if not for anyone else in the room. But for the spherical harmonics, we have L equals 0 shown at the top, which is the monopole, which is constant. And what's powerful about spherical harmonics is that they can be used as a basis to describe any function on the surface of the sphere. And so, then they describe variations on different spatial scales. So L equals 1 is the dipole, and I'm showing here down to L equals 4, where you can see as we increase in L values, we're decreasing the spatial scale on which we have variations in our function. Okay. So what does this look like? Here I'm showing you 3 velocity maps of a shell from Nico Garavito-Camargo's simulations, where these are again n-body, just containing a Milky Way and an LMC. And here I'm showing you the radial velocity map this is just a spherical shell centered on 45 kiloparsecs. The radial velocity is shown on the left. The polar velocity is shown in the middle. And the rotational velocity map is shown on the right. And so each little pixel here is showing you, it's color-coded by the mean velocity in that component of motion at that position. And so just for the record, initially, in the absence of an LMC, an isolated Milky Way would be completely smooth in all of these different features, in all of these different maps. And the position of the LMC I've indicated here with the stars. Then we have the L equals 5 spherical harmonic expansion shown here on the bottom. And so what we can see is that our relatively low order spherical harmonic expansion is able to pick out the relevant features, the salient features in these velocity maps. So just to talk a little bit about what those are, if we look at the radial velocity map, here is the position of the LMC, and it's moving outwards, which is why it's color-coded yellow. And we can see that there's this yellow blob trailing the LMC in its orbit. And those are stars that are trapped in that traditional Chandrasekhar dynamical friction wake that are trailing the LMC in its orbit. And we also have stars that are moving net outwardly in the north as a result of this modal response of the halo. In addition, if we look at, and that's captured by the M equals 2 mode here in the low order spherical harmonic expansion, where we have these radial velocity net outward motion on both sides of the galaxy. Then, if we look at the rotational velocity map, we see these converging motions. We see that it goes from blue to yellow in this map. This is symbolic of this is showing converging motions trailing the LMC in its orbit. And so these are stars that are again accelerated towards the orbital path of the LMC and are contributing to this dynamical friction wake trailing the LMC in its orbit. So this is nice that we see that a low order expansion is capturing the features in this map, but what we really want to do is put a number on some of these things. And so we can use the angular power spectrum in order to quantify and then ultimately have a way of measuring these different patterns that we see in the simulations. So here I'm just showing radial velocity maps at 3 distances out into the halo. So we have radial velocity at 45 kiloparsecs, 70 kiloparsecs, and 100 kiloparsecs. And the power spectrum for each of these maps is shown on the right-hand side, where purple is 45 kiloparsecs, orange is 70 kiloparsecs, and blue is 100 kiloparsecs. And what we see here is that as we move farther out into the halo, we have a radial velocity dipole that is increasing as a function of distance. And the angular power spectrum gives us a way of quantifying that. And this is consistent with a later paper that Nico wrote that I contributed to on using basis function expansions to characterize the density wakes in his simulations. But he found, here if we have a radial velocity dipole in all of the simulations, as a result of this interaction, there's a radial velocity dipole that increases as a function of distance he tried 4 different massless LMCs. And this is indicative of the fact that the center of mass of the Milky Way the Milky Way disk has been dislodged from the center of the Milky Way outer halo. And so you have this perceived net motion of the outer halo with respect to the inner halo, and that's this reflex motion. Furthermore, we can use the angular power spectrum to demonstrate the fact that different mass LMCs will have different influence on the Milky Way's velocity field. So here I'm showing you the radial velocity maps for the least massive LMC that Nico tested, which is 0.8 times 10 to the 11, up to his most massive LMC that he tested, which is 2.5 times 10 to the 11. And we can see that while the shapes of the power spectra are pretty consistent, the magnitude scales with mass as we would expect. So this is all fun, but I motivated this by saying that we know that there's disequilibrium on small scales as well as large scales in the Milky Way. So can we use spherical harmonics to deal with the fact that we have substructure in our galaxy? So to test this, we looked at the Bullock and Johnston simulations, those first simulations that I showed you at the very beginning of the talk, where these are again purely accreted stellar halos onto a Milky Way like parent potential. Because the Milky Way is modeled just simply as a potential, there's no live dark matter halo. There are no dark matter wakes in these simulations, so we can just test accreted substructure. And to look at this, I focused on what I call like the extreme accretion histories from Bullock and Johnston. So in Bullock and Johnston, you can construct a halo purely from really early accretion events or purely from really recent accretion events. So those are shown here in the middle panel, a velocity map for the halo constructed from material that's only accreted very early and has had a lot of time to phase mix in the galaxy versus material that's accreted really recently that still has a lot of kinematic coherence. In addition, you can construct a Bullock and Johnston halo purely of very massive accretion events, which is shown here in the upper left, or purely from low mass satellites, which is shown on the lower left. And so what we see when we compute the power spectra for these maps, here I'm showing you the power spectrum for the range of power spectra from Nico's LMC only simulations in the purple shaded region. But we have, and in general, we see that these halos are contributing more on smaller spatial scales, so higher L values than the LMC simulations in general, all of the Bullock and Johnston halos do. At low spatial scales, in general, there's not a lot of competition for the L equals 1, L equals 2 power, except for the halo comprised entirely of recent accretion events, which is shown here in pink, as well as the halo comprised only of high luminous satellites, which is shown here in gray. So the good news for us in the Milky Way is that we don't think the Milky Way has had a particularly active, recent, massive accretion history. So maybe this isn't a problem for the Milky Way. But there are 2 exceptions to that statement I just made about the Milky Way having a quiescent recent massive accretion history. one of which is the Large Magellanic Cloud, that is this huge, massive thing that's in the process of disrupting in the Milky Way. And the other one is Sagittarius, which is the most massive stream in our galaxy. So here I'm showing you the beautiful map of Sagittarius as seen in RLRA stars from Pan stars. Sagittarius has debris all over the sky. We've discovered debris out to over 100 kiloparsecs. And so Sagittarius is kind of famous for confusing basically all Milky Way halo studies and has to be accounted for when doing substructure studies in the Milky Way. So to understand how Sagittarius might influence our analysis, we took 2 models of Sagittarius and injected it in the LMC only simulations. So just to be clear, this is actually a very simple painting on of Sagittarius onto the LMC only simulations. These were not run together, so the LMC and Sagittarius are not interacting in these simulations, but this will give us a 0th order idea of what to expect in terms of how Sagittarius might be contributing to the signal and might be confusing the signal from the LMC. So here I'm showing you again the 3 components of motion, 3 maps for the LMC with the Sagittarius model painted on. And the Sagittarius model I'm showing you here is from Dennis Urkel. And so on the bottom panels, I'm showing you the power spectrum. So the solid line shows the power spectrum combining Sagittarius and the LMC. The dotted line shows the LMC only, and the dot dash line shows the difference between the 2 models. And so first, I just want to say that for the difference between the 2 models, I'm only showing you the differences for 70 and 100 kiloparsecs because the signal is so much stronger for the LMC only. The Sagittarius model is not overwhelming at all, not even coming close to competing with the signal from the LMC in the outer halo. In the inner halo, we can see that the contribution is significant. And I said inner halo, this is 45 kiloparsecs. This is still pretty far out. But at 45 kiloparsecs, we can see that Sagittarius is contributing significantly, but it's still not overwhelming the signal from the predicted signal from the LMC. So my takeaway here is that we should model Sagittarius's influence, but based on this analysis, it doesn't seem that Sagittarius is likely going to completely overwhelm the signal predicted from the LMC, which is reassuring. So to summarize part 1 of my talk, the LMC is predicted to induce a dark matter wake in the Milky Way halo, and that this in turn will affect the stellar halo. And we could potentially use spherical harmonics as a tool for disentangling and characterizing kinematic variation in the Milky Way halo. We know that debris from recent massive accretion can cause large power over large spatial scales, similar to what we expect from the LMC, similar at least in magnitude to what we expect from the LMC. But when we looked at Sagittarius, a model for Sagittarius, the massive stream in our own galaxy, we found that while we should model it and worry about it and care about it, it should not, from our analysis, overwhelm the signal predicted from the LMC alone. So since I wrote this paper in 2019, there have been a number of really exciting observational results that I want to mention. So first of which is there was this great Nature paper from Charlie Conroy's group claiming the detection of the overdensity trailing the LMC in its orbit, which is very exciting. They found this morphology of this wake that looks very similar to the predictions from the simulations, which is really exciting. In addition, there was this measurement of the reflex motion induced by the LMC on the Milky Way disk and halo that was measured by Peterson and Penarubia, and see also results from Dennis Urkel. So this is all really exciting. We're getting a better handle on what's going on in our galaxy and trying to understand what's coming from the LMC. But I also want to have a word of caution, which is that we're working on it. We have yet to detect dark matter wakes in cosmological simulations in this realistic environment. And so it's critical that we test these observational techniques and these observational analysis techniques in a cosmological halo where we have all these complications that are not included in an LMC only simulation. So this is work that's being led by Alex Riley, who came to Flatiron to work with me at the CCA Dynamic Summer School. And we've been working on a project that Alex has done a fantastic job of leading, of studying velocity dipoles. So this is looking for, using the Peterson and Penarubia method of measuring reflex motion in latte halos where there is an LMC analog. So this provides us with the opportunity to test this method in a realistic setting. So here I'm showing you a very beautiful real color image of one of our simulated LMC Milky Way pairs. And so what Alex is finding is that he's looking at the magnitude of a velocity dipole measured over time, where white is its pericentric passage, red is into the future, and blue is into the past. So this is the orbit of the LMC analog. When he measures the magnitude of the dipole, or sorry, when he measures the direction of the dipole, he finds that the dipole is pointing back to where the LMC was in its orbit, and it continues to point away, point in that direction, point to where the LMC was as the LMC has passed pericenter, which is consistent with the result from Peterson and Penarubia, who find the LMC, if we just go back, I can show you that the magnitude of the dipole is oriented towards where the LMC was in its orbit before pericenter. So this is an exciting confirmation of their results, but we also have found that substructure, in particular substructure that we might not have discovered yet in our own Milky Way halo, can bias the results and can lead to the conclusion that there is this large scale reflex motion even when there isn't in the halo. And so Alex is writing up these results, and so stay tuned for more details on that. And then finally, I just want to advertise that I think this problem is a really great opportunity for Rubin and Roman synergies, because the predictions from the simulations, the tangential motions, are really interesting, where we can use Rubin to study the large scale proper motion structure in the halo, and then complement that with Robin to do very detailed studies of the tangential motion in the halo. In particular, here I'm showing you the rotational velocity maps from the Garavito Camargo et al. Simulations, where we can look at the large scale features as well as these smaller scale features in detail with Roman Space Telescope. So it's a very exciting Rubin-Roman synergy problem. Okay, so summary of part one. We've talked about the fact that spherical harmonics might be useful for quantifying the effect of the LMC, but looking forward, we need to test weight predictions in cosmological simulations, and in particular, analysis methods for inferring weight properties in a realistic setting. And we're really excited about what's going to come on the data side for the future with Rubin Observatory's LSST and Space Telescope. Okay. So now that we talked about the Milky Way dark matter distribution and using halo stars to study the dark matter distribution in our galaxy, I want to switch gears and talk about the dwarf galaxy progenitors of the Milky Way stellar halo and how we can use halo stars to learn about these systems that contributed to the buildup of our galaxy but did not survive until present day. So to motivate this, I want to start by showing you here these two images where I call these plots of the formation histories of two latte galaxies. So what do I mean when I'm saying I'm showing you the formation history? So in each of these panels, what you're really looking at here is a 2D histogram of the formation time versus formation distance of every star particle in the simulation. So what's going on here? You can see that there are these bright bands at the bottom of these plots, which are at low formation distances over time. So time, 0 is the beginning of the simulation, 13.7 is the present day. So these thick regions, overdense regions on the bottom of these plots are star particles that are forming in the disks of these simulations. In addition, we have star particles that are forming in dwarf galaxies and other galaxies as these streaks that are out at larger distances. So here I've highlighted a particular case where we have a surviving dwarf galaxy that's inside the virial radius of the host at present day. It's still forming stars, but it hasn't yet directly interacted with the Milky Way. And these are other, local satellites or local dwarf galaxies. But we also have accretion events. So here in M12R, we can see that we have these thick streaks that hit the Milky Way, that enter the Milky Way at late times and are interacting at late times with the galaxy. And so these are recent massive accretion events. So we have these thick bands that come in at late times. And then if we look at the other galaxy, M12M, we see that there aren't those thick streaks at late times. Instead, we have some action very early in the simulation for this galaxy, where we have a lot of material coming in very early, and the disk forms much earlier in M12M than in M12R. Okay, so we have these two galaxies that have these very different formation histories. M12M is characterized by very early accretion, whereas M12R's is characterized by this late time, really massive accretion. And so in terms of observable differences, like how can we go to our observations and tell the difference between these two galaxies? And there are a lot of ways to answer that question, but one way that I want to focus on in this talk is their chemical abundance ratio distributions. So that's a mouthful, but the acronym I'm going to use is CARDS. When I say CARDS, what I really mean is the distribution of stars in the, for the purposes of this talk, magnesium on iron versus iron on hydrogen plane. So if we look at the distributions of stars in this chemical plane in magnesium on iron versus iron on H, we can see just with our eyes that these two distributions immediately look very different from one another. So why is this? What's going on here? So to help build intuition for what we're going to see in the rest of the talk, I just want to back up for a second and show this extremely useful figure from Jennifer Johnson about the origin of solar system elements. And I want to highlight the elements that we're going to talk about in today's talk. So first we have magnesium, which is believed to be produced almost entirely in type 2 supernovae in exploding massive stars. And then we also want to talk a lot about iron today, which is produced in exploding massive stars, but also in exploding white dwarfs. Iron is produced in both type 1a and type 2 supernovae. Now, this is really useful because these elements are tracing chemical enrichment on different time scales. So because we have magnesium, which is tracing primarily type 2 supernovae, and we have iron, which is tracing both type 1 and type 2 and type 1a supernovae, and type 1a turn on much later in time, they occur on a longer characteristic time scale, we can use these abundances to tell time within a dwarf galaxy. So here, just to motivate this a little further, I'm showing you what's now called the Tinsley-Wallerstein diagram for how alpha, or magnesium, for the purposes of this talk, I'm only talking about magnesium, but how alpha elements produced in type 2 supernovae over iron versus iron on hydrogen involve in time in a dwarf galaxy. So at first, there's a relatively constant fraction of constant ratio of alpha to iron until the type 1a turn on, at which point the distribution will turn over because the galaxy is now enriching more in iron relative to alpha. And how far it gets over before it turns over is related to the mass of the system, because if the system is forming a lot of stars at early times really fast, really efficiently, it'll form a lot of stars and enrich to high metallicity before the type 1a's turn on. Whereas if you're forming stars less efficiently, your turnover in this distribution will occur at lower metallicity. Okay, so we have this picture in mind. We can look again at these distributions from fire. So if we look at these distributions, we can see in M12M, which is characterized by really early accretion events, mostly early accretion events, that the density in this distribution is relatively at low metallicity and higher magnesium on iron abundances compared to M12R, where M12R is characterized by very late time accretion and massive accretion, where its abundance distribution extends to higher metallicity, and you see this turnover in magnesium on iron versus iron on H at higher metallicities. So this is the way in which the distributions are encoding information about their assembly history. The abundance distributions are encoding information about the assembly history. So the goal that we had was to ask the question of, okay, we can see with our eyes that these different formation histories are leading to different abundance distributions. How can we go from this abundance distribution to making quantitative inferences about the galaxy's assembly history? So specifically, when I say assembly history, much of what we want to know is what is the mass spectrum of accreted dwarfs, by which I mean what fraction of the Milky Way's mass came from dwarf galaxies of a given mass. So how much from low mass events versus higher mass events. And then we want to know about when the Milky Way assembled its mass. So did it accrete most of its mass early or late, etc.? And how can we make these quantitative statements based on the abundance distribution? So to test this, we tried this method that's called the CARDS method that was first proposed by Duane Lee. And the idea behind this method is that we can use empirical templates of dwarf galaxy abundance distributions as a basis for describing the overall abundance distribution. So there's a whole lot going on in this plot. Don't panic, I'm going to talk you through it. So this is the technique, again, that was first proposed by Dwayne Lee and Catherine Johnston in 2015. But at that time, they were working purely with the Bullock and Johnston simulations that had no self-consistent chemical enrichment. So it remained inconclusive how well this would work in a realistic setting. So in this grid of templates that I'm showing you here, this is a grid of dwarf galaxy abundance distributions where we're going from top to bottom, we're increasing in stellar mass. So the top row are templates for relatively low mass, so stellar mass of 10 to the 6 to 10 to the 6.5 accretion events, down to total stellar masses of 10 to the 8.5 to 10 to the 9. As we go from left to right in this grid of templates, we're increasing in quenching time. So templates on the far left-hand side are for dwarf galaxies that quench within the first 2 gigayears of the simulation, whereas templates that are on the far right are forming stars throughout the entire simulation. So if we zoom in on a particular template, so this is the template in the top left. So it is a low mass template that it's a template for a galaxy that is low mass, so 10 to the 6 to 10 to the 6.5 in stellar mass, and it quenches early in the simulation. So we see it's very alpha enhanced. It doesn't extend to high metallicity. This is what the distribution looks like in fire for a system like this. In addition, we can look at these higher mass systems that quench late. So that's what's in the lower right panel of this template. So this distribution, you can see it extends to high metallicity. The distribution turns over as a result of enrichment from type 1As. And this is a system that's forming stars basically up until the end of the simulation. So the idea behind this technique is that we can use these individual templates as the basis for modeling the full abundance distribution. So in this context, we can take our full halo and we can write it down as a linear combination of these different templates, where the coefficient that goes with each of these individual templates, in theory, corresponds to the fraction of mass or the fraction of stars to the total stellar halo that came from a dwarf galaxy with this mass and quenching time. And so this is the CARDS framework, but we didn't know if it was going to work because it hadn't been tested in a cosmological setting. So really the fundamental question here is, if you have a dwarf galaxy with a given mass and quenching time, can you accurately predict its abundance distribution? If the answer is yes, then you're set. If the answer is no, then it's more complicated. So I'll get into that. But before I get into the details, I have to acknowledge that this work would not be possible without the work from Nand Paneetan-Faisal, who is this awesome grad student at University of Pennsylvania, working with Robin Sanderson. He wrote a really cool paper on streams in the fire simulations, and he has this catalog that's publicly available. So if you're interested in playing with streams in fire, you can go check it out on FlatHub. So please check out Nand's paper, and his work, and collaborating with him has really enabled all of my work in the fire simulation. So I'm very grateful to him. I think he is maybe coming up on the job market, so keep an eye out for him. He's awesome. Okay, so I relied on Nand's characterization of streams, space mixed debris, and satellites to create these templates. I also have to have a disclaimer here. I don't know if there might be some observers in the room who are looking at these distributions and see that they look kind of weird compared to what we see in the data. So these templates are not intended for use with observational data. And so just to emphasize that, here I'm showing you an abundance distribution for a disrupted dwarf in latte, compared to one of similar stellar mass of sculpture in the observations, and you can see that they look super different. One reason for this is that dwarf galaxies in fire are too metal poor compared to observations. So this is a well-known result. I'm showing this from Nand's paper, where the observed mass metallicity relation is the black line, and the fire mass metallicity relation is shown here by the colored points and the gray lines. And so we can see that they're not consistent. We haven't yet nailed down mass metallicity in the fire sims yet. And one reason we think this is true is a result of the delay time distribution from type 1A supernovae. So I just want to emphasize that Pratik Gandhi, who's a grad student working with Andrew Wetzel, wrote a really nice paper on this recently, and found that you could tweak the delay time distribution to make it more realistic, and that this made significant improvements in the mass metallicity relation in FIRE. But I also want to emphasize that there's the new FIRE 3 physics model that's just coming out, and the new runs that are just finishing, where they've made significant improvements to the chemical enrichment and stellar physics in the simulations. So we should be seeing exciting things there. But I just want to say, you know, it's okay with me that these templates aren't safe for use with observational data yet, because that's not really the point of this paper. The point of this paper is to say, if we have reasonable templates in FIRE, can we recover the assembly history within FIRE? We have galaxies we have a stellar halo and dwarf galaxies that are formed in the same universe, and that's what we care about. So in principle, if we find that this CARDS method is working in FIRE, that gives us more confidence that it'll work in an observational data if we have observational empirical templates. So we tried to address a few questions in this paper, but the one I want to focus on today is just how well does this technique work in a cosmological simulation? Can you do this at all in the cosmological simulation context? And so, as I mentioned earlier, the fundamental question here is that if you have the stellar mass and the time that a dwarf galaxy or halo progenitor took to form its stellar mass, can you predict its CARD using empirical templates from present day dwarf galaxies? And what are the limitations of this? So in response to the question of does this work, the answer is sometimes yes. So this is a success story. This is the M12F halo from the FIRE suite, where we find that the linear combination of templates that we construct from present day dwarf galaxies in the simulations is able to do a good job of reproducing the abundance distribution of the halo. So the simulation abundance distribution is shown here on the left. Our model abundance distribution constructed from the templates is shown in the middle, and our residuals are shown on the right-hand side. And we can see even by eye that this is a good model for the abundance distribution. The residuals are low. Our empirical templates have done a good job of describing the distribution. But what does this mean for the assembly history? So here I'm showing you the assembly history of this galaxy, which I've broken down into the mass spectrum of accreted dwarfs on the left. So the y-axis here is the fraction of mass that was accreted by this halo as a function of its dwarf galaxy progenitor mass. And the results from 3 different template sets are shown here by the colored dots, and the residuals are shown in the bottom panel. As you can immediately see that the mass spectrum of accreted dwarfs is recovered for this halo very accurately, which is really exciting. So this one is actually recovered within like 3%, which I was pretty pleased about that. In terms of mass accreted as a function of punching time, the residuals are higher. It's not as constraining as the mass spectrum of accreted dwarfs. But given that, I haven't emphasized this enough actually, given that this is a model that purely consists of empirical templates and no prior information, I'm pretty happy with this. You could imagine this is almost like the worst we could do, because you could incorporate more information from cosmology about when we expect mass to become minimum. You could incorporate more information about, prior information about the mass distribution of dark matter. And so this is really a baseline. So this is just a model, the results from a model with the full abundance distribution and a set of empirical templates. And fortunately, this M12F success is not unique. So for 4 out of our 7 simulations that we worked with in this study, we found that we could successfully recover the mass spectrum of accreted dwarfs to within a precision of 10% using our dwarf galaxy template sets. So this was exciting to me. This was very reassuring. But I wouldn't be honest if I didn't also talk about our failures. We had success, but we had failures too. So this is my example failure story from the Halo M12C. And we have here simulation abundance distribution on the left. We have our model abundance distribution in the middle, and our residuals are shown in the far right panel. And we can immediately see that the dwarf galaxy templates are not doing a good job of reproducing the abundance distribution in this halo. In particular, if we look at this distribution, it's got a really bright high overdense region right here at a metallicity of about -1 and an alpha of about 0.2. And this bright overdensity is not, consistent with the dwarf galaxies. that contributed to the buildup of the template. So this is an example of the CARDS method not accurately inferring the abundance distribution, and therefore also the assembly history. So if we look at the assembly history, the mass spectrum of accreted dwarfs here on the left, we can see that it's way off, basically because there's this high overdense region at metallicity of -1. What's happening is that this system is more massive than its abundance distribution thinks it is, because it has this burst right here, and so it's not enriching to higher metallicity. It has a burst fairly constant metallicity. And so the mass spectrum and the mass accreted as a function of quenching time is not accurately inferred. But the good news is that our first sign that things have gone awry is the fact that we have these significant model residuals. We can immediately tell that our model is not a good fit to our data. And so we can quantify this, where here I'm showing you on the x-axis, the dispersion in the model versus the data residuals for the full abundance distribution. And then in the top panel, I'm showing you how accurately the mass spectrum is inferred. And on the bottom panel, I'm showing you how accurately the mass as a function of quenching time is inferred. And so here, if we have our failure case M12C, we have both high residuals in the abundance distribution and high residuals in how accurately we're inferring the assembly history parameters. But then if we look at M12F, these are the green points down here. We have low residuals in our model and low residuals in our inferred properties of the assembly history. And so the fact that we see this general correlation, there's some exceptions, but generally we see this correlation is a good sign. And that would also be a very interesting result if we found that the progenitors of our halo could not be accurately modeled with present day dwarf galaxies. This would be an interesting result in the Milky Way. So just to summarize part 2, the chemical abundance ratio distribution of stellar halos is rich with information pertinent to its formation history. And we can model the CARDS as the halo as a linear combination of dwarf galaxy templates. And we're able, in some cases, to recover the mass spectrum and quenching times of accreted dwarfs, which is really exciting. But if we have a situation where the CARD templates are not a good representation of the progenitors of the stellar halo, then this technique will not work. However, that would be indicative that something is interesting, is going on. And so there's still these interesting links between formation history and abundances. I'll just close out real quick by saying it's such an exciting time to work on this in the observations. There's a huge effort right now, including, of course, with SDSS-5, which I'm involved in, to measure abundances of halo stars and to use these abundances to make inferences about the dwarf galaxies that have contributed to the buildup of the Milky Way and M31. So it's a really, really exciting time to be thinking about what we can do with all of these abundances. So CARDS is just one piece of this puzzle. So I'll leave my conclusions up and take questions. Thanks.
All right, thanks, Emily. Let's all give Emily a hand for a very good talk. And Yanshin, I see you have your hand raised, so go ahead.
Hi, Emily, nice talk. So I was a little bit confused when you're trying to use CARD to infer the merger histories, so the dwarf galaxies being incorporated into the big galaxy. Is this a reverse process or is it a forward process, meaning that you're making it as a linear combination, but your templates are not orthogonal to each other? So if you want to just decompose the bigger galaxy, is the solution unique? And if it's not unique, you're just doing it forward?
That's a great question. Yes, we're doing it because it's just a linear model for how we've set it up. You're right that they're not orthogonal, but in the way that we've set it up, because it's just a linear model, yes, the solution is unique. What we did not explore were perturbations to that and explore how much the answers varied if we made slight variations to our template set or incorporated, observational uncertainties or other effects. But yes, given a template set and an abundance distribution, as we set it up, there is one unique solution.
Because I guess I understand why it's unique then. Can you explain that a little bit more?
I mean, just in the fact that it's a linear model, so there's only one set of coefficients that can go in front of each template. yeah, it's just the linear model that we solved from the optimizer using an optimizer. And so it's the same, I guess, as linear least squares. We have I guess I don't quite know. I feel like you've asked me a deep question that I'm not giving a deep answer to, but yes, there's only one solution given a set of templates, but I think there will be more than one solution if you incorporate perturbations to those templates or observational uncertainties.
Okay, all right, thanks.
Thanks.
Question?
Can I ask one? I'll just ask. Okay, sorry. So I think my question is probably similar to Yanqing. So you are saying the failure ones examples are not caused by the degeneracy, but because of the templates that you are using doesn't, like the template you're using are from the redshift 0 dwarf galaxies, but they are not kind of similar to the disrupted dwarf. Is that correct?
That is correct. So I can show you just a little more detail. This one here, the M12C stream, has this really interesting abundance distribution where it has this starburst here. It's actually induced by its first pericentric passage. And so if we compare that to, for example, one of our surviving dwarf galaxies, it just hasn't experienced anything like that. And so that event will not be well represented in our template set. So yeah, it's not that's the reason that there's the failure case. So it still solves the model. It just gives a solution that is not a good, the best fit model is not a good indication of the data. Yeah.
Okay, I don't know how much will help, but one suggestion I would have is, so I know you are trying to use the intact dwarf at redshift 0 as template to kind of figure out the mixed halo, but there's from Nance work, there's also stream. So I don't know if you use that part. So not the intact galaxy, not the fully mixed halo, but the stream, and just adding that as another template and see if you can solve the problem. But maybe it's hard because if some of the galaxies, disrupted galaxies are very kind of unique in its early time, then it's probably hard to solve this problem. But that's
yes, I didn't have time to talk about that today, but we did explore that pretty extensively in their paper in terms of swapping out, like, what if we only used streams and phase mix debris as our templates? What if we swap out the different populations? And we found, in general, that the dwarf galaxy templates performed as well as our stream and phase mix templates, which was not necessarily a result we were expecting. But you're totally right that that's absolutely relevant. Yeah, we have, on the other side, this is a stream in M12W. And when you try to model the M12W stream using this M12C stream as a template, it's going to be a bad match. So, yeah. Thanks, Tim.
Thank you.
Okay, Ted, I see you have your hand up.
Yeah, I think Ting kind of asked you what I was going to ask you, so I guess I'll try and think of something else. But you mentioned that you're kind of not worried because, like, you're kind of matching like for like in terms of, like, you're just doing simulation dwarfs with this. So my question is, I guess, like, what do we need to do, or like what is needed to be able to do this with observational data? Like, have you tried running this just on what we have from Apogee, for example? Does it work at all, or does it just fail?
So I would be terrified to apply the FIRE templates to Apogee for the reasons we described, but I think, if I go back, we have some cards from Apogee that we could start playing with. I also think it's going to be important for, I know Subaru PFS is interested in targeting the outskirts of dwarf galaxies and getting the full populations in dwarf galaxies. I think that's going to be important. So I think we're close. I think we just want a range of dwarf galaxy masses and formation times. And we've made a lot of progress on the survey side in terms of accumulating that data set. One avenue that I'm really excited about is like a hybrid template set, where there's this new functionality for the FIRE 3 simulations that's called the age tracer model. And it will actually let you tune in post-processing your yields to match. You could tune a set of dwarf galaxy templates in the simulation to match a set of observed dwarf galaxies. And then you could kind of fill in the gaps with your simulation templates. Now there's assumptions in that, but that's, to my mind, an intermediate step before we have a full, before we have all the dwarf galaxy observational templates that we would like.
Right. All right, I see Peter's got a hand up, but just another quick one is, so like, you're using the current I think this is kind of what Ting was asking as well, is like you're using the present day intact dwarf galaxies. Like we probably know that the very earliest accretion events onto the Milky Way looked very different to the satellites that we see now, which is part of the exciting thing about being able to find like Gaia Enceladus or whatever.
Yeah.
So have you
I think I have
looked
a
in
backup
Gaia?
slide.
Maybe
So I think I have a backup slide to maybe address, maybe this is what Ting was getting at, to the fact that that dwarf galaxies, present day dwarf galaxies, and streams or debris that's been phase mixed are evolving on different timescales. And so in our templates, the way that we account for this is by taking, for a template for something that's only formed 2 gigayears of stars, we use only the first 2 gigayears of stars. We use only old stars from things that then enrich farther. So for a template for something like Gaia Enceladus, that would be something that is very massive at present day and is also, you know, massive at earlier times. So that's how we trick, that's the trick that we use in the templates to make these more consistent comparisons.
Okay, cool.
Does that
Okay,
make
yeah,
sense?
that just showed that I haven't read your paper in anywhere near enough detail. So, okay.
That's a very nuanced point.
That's great. Thank you so much. And thanks for the nice talk. Thank you.
Thanks.
Peter, you can go ahead if you want.
Thank you. Thank you for the talk. You told us about the LMC getting more massive in our analysis, or our understanding of it in the first passage and so on. What has changed about the SMC?
Great question. So I am not as much an expert on the SMC because I haven't studied the Magellanic system in as much detail. I'm not an expert in modeling the Magellanic system. I'm more interested in what they're doing to the Milky Way. So I'm going to have probably an incomplete answer for you on that question, but the more massive the LMC gets, certainly the more massive the SMC gets as well. And so I know there's a lot of discussion in the field about how many interactions the SMC and LMC have had, to what extent their interaction is causing star formation or features in the gas around the Milky Way and the Magellanic stream, the Magellanic gas stream. And so I think there's still a lot yet to be resolved about the interaction history between the LMC and the SMC and the implications for that in present day observations of the Magellanic clouds. So I think I have an incomplete, the answer is I don't know entirely the whole history of the SMC's characterization, but I know that there's a lot of exciting work going on regarding that and regarding the evolution, the orbital history of the two clouds together as a system.
I'm glad you mentioned the streams, the Magellanic streams, which are actually gas. I guess.
Right.
Are they just a curiosity, or can you learn something from them too, from the gas?
I think you can absolutely learn something from the gas. And so I know there's some exciting work from Ellen Adonki's group at University of Wisconsin-Madison, where a grad student of hers, Scott Lucchini, had a Nature paper recently where they found that they included this massive gaseous corona around the clouds, and it immediately addressed many of the outstanding issues for modeling the clouds, including the mass budget. And it was also has some exciting observational implications for looking for gas that's much more nearby than has previously been associated with the clouds. So I think, yeah, the LMCs, the Magellanic clouds are one of the really exciting places to study gas and dwarf galaxies and gas and galaxy formation in the Milky Way. As I understand it, as someone who doesn't work on gas.
If I could ask one more, how do high velocity clouds, which are again gas, and not identified in particular with stars, how do they relate to this picture? Can you see some relationship in the fire simulations or anything else?
That's a really good question that I honestly don't know the answer to, but I am tempted to Google immediately after this to just have a look at ADS and see if high velocity clouds are resolved in fire, because I've never really focused on the gas in the simulations. I don't know the answer off the top of my head.
Thank you. All very interesting.
Thank you.
Okay. If there are no more questions online, there's none in the room. So let's give Emily a hand one more time. And
Thank you all
we're
so
done.
much for having me.